I'm Alex Brown, and I'd like to introduce you to the Bare Deck Wall Anchorage Design Tool. This tool quickly and thoroughly checks for both combined axial tension or compression with combined bending and web shear. It also checks the connections for shear and tension, including combined shear and tension interaction at supports. Web crippling is also checked at supports for inward loading. All of this in service of using the metal roof deck to brace a concrete or masonry wall against out-of-plane forces. Let's jump in. First thing you'll notice, looking across the top of the page here, are the different tabs. So a lot of these get into the calculations that power the tool, just showing every step of the way, documenting all of that for easy access and transparency. We'll go through all of those here one by one in a little bit. I do want to point out the print button here. So this will generate a PDF download that will give you, in the case of the summary tab here, it actually is the bottom half of the tool, showing all of our inputs and then the various checks that happen. So the inputs and outputs all in one spot. And then for some of these calculation tabs, it'll just show all the multi-page calculations and the equations that are happening. And then I'd also like to point out, this tool does not check service load deflection of the steel deck, nor does it check load combinations that don't consider axial loads, but that might govern if there are large gravity or vertical inward or outward wind loads. So very specific usage here. But scrolling down a little bit, it's a lot of inputs. It might be a touch overwhelming at first glance, but what we're really trying to do is just capture all the demand that this system needs to handle. So that's this first part here is the different loads that are being applied, the anchorage forces for wind and for seismic. And then this bottom portion is what's resisting that. So the different products, the spacing, the geometry, bearing, the different connections, all of that gets documented here. And then we're going to calculate those capacities compared to the demand, and that's where this summary of calculations comes from. So going through the rest of the tabs here real quick, this prying action tab here, what this tab allows you to do is calculate the prying action displacement based on your expected diaphragm deflection. So this would be previously calculated during your design process, and then based on your roof height and that eccentricity, the E value for the connection between the deck and the ledger, that is going to generate what that expected prying action is going to be. And then this number, X, would be inputted back here in the prying action for either seismic or wind. So that's where that input would actually go to incorporate it within the design. The next couple tabs are just all the different calculations for the different checks that are happening. So first one is axial and bending. So all of that is shown here. So again, that's taking all of those inputs from the summary tab and then sort of running it through its paces and giving you full visibility on what's being calculated and how. So that's for the combined axial and bending action. These are for the connections at the walls. And you'll notice that the support connections are all listed here along with the assumed values that each one has from the different manufacturers. So that's listed up top and then again, showing what those calculations are. So that's at the wall connection, and then this is for the field connections. The next tab, J and M derivations, are the shear and moment diagrams. And this just documents how we derived those interactions when axial forces are present. So you can see the P listed there, and then kind of how we interpreted that, where those equations came from. All that is listed here, nothing to interact with, it's just for reference. Similarly, this attachment patterns tab, just for reference, showing the different deck profiles and widths that we have for our various products. And then when we say something like 36.4, just graphically showing where those 4 attachments are made across the 36-inch width. So going back to the summary tab here, I'm going to be pulling from an example from our roof structure design guide written by my colleague Pat Bodwell. So that's available as a free PDF download here at vercodeck.com. And if you're following along, this is from chapters 6 and 8, getting into the seismic and wind diaphragm and wall anchorage calculations. And this example is assuming a single-story roof, 151,000 square foot warehouse on the west coast of the United States. So with that example, we're going to start punching in some of the values that were calculated previously. So there were 5 PSF and 2 PSF for inward and wind uplift load combos specifically. Roof live load was 20. We did not have any snow or rain. Wind uplift on the steel deck was calculated as 25.3, and then same for the wind uplift on connections. Wall inward wind anchorage force was 423. This was 342, and that notional load was 124 PLF. That seismic wall anchorage force, 1,985. That had to be resisted, and an SDS of 1. A seismic design category, fine, C, D, E, or F. Though you can see A and A or B also listed here. And then the wall construction type, concrete or masonry, or other. So we'll leave these as the default values. For this anchorage load here, you can see a note that the 1.4 increase is something that we will take care of. That comes from ASCE 7. You can see the reference there. You do not need to include that in your input. That is something that we can multiply, and that'll be included in our calculations. So then scrolling down a little bit further here, for the deck options, for this dropdown, this tool can handle acoustic roof deck and also non-composite and composite floor decks without their concrete fill, so just the bare deck. All of that can be analyzed. We'll leave it as roof deck, PLB 20 grade 50, 8-foot spacing, all of that's fine. Though that deck bearing will adjust slightly to 2. And then for the connection types, this example used the Hilti HSN 24s. So we'll get that in there, grade 50. For the supports, 1/4 inch is fine. 36/7 pattern. So this prying action was calculated in that example to be 0.01. So we'll get that. So that was at the wall connection. In the field of the diaphragm, some of the same things, still using Hilti HSN 24, grade 50. We'll drop that support member thickness down to an 1/8 inch, just to be a touch conservative because we don't know how those joists are going to be designed yet. Deck end condition, both ends lapped, though this tool does support butted ends or a combo, one end butted, one end lapped. 36/7 at the end connection, 36/4 in the interior, that's all good. And then based on all these inputs, the summary of calculations is really demonstrating the power of this tool by showing everything passes. Great, and I can see very clearly the 1-span, 2-span, 3-span deck conditions, the different checks, so combined axial and bending, the connection strength, the web crippling at the wall and in the field. So all of that is visible here, and I can see very quickly at a glance that, yep, this arrangement is going to meet my required loading, and everything looks good. And at the end of this process, I've got this readout here, so that'll be a 1-page printout by hitting the print button there. And that's the bare deck wall anchorage tool. It's an exceptionally powerful tool, taking a series of material property lookups and complex equations and transforming it into one simple check. And with that, happy specifying.